So the topic today I'm going to discuss is glass in earthquake. So it's a presentation on use of glass in earthquake prone areas. So I am architect Bharath Gowda. I'm an architect and a structural consultant. So the brief overview of the session would be is I'll try to cover the session in like 45 minutes plus or minus. So there will be three parts to this session. One would be a brief history of glass in modern buildings, modern building application. Here I'm going to go over a brief history of not necessarily all the way to old history, but contemporary, how the glass came into existence and how building evolved. So this, and I'm going to show some of the projects that I have been involved in. I had the opportunity to work in India as well as in the United States. In fact, most of the project I'm going to show in glass is going to be the work that I did in the United States. And I'm going to discuss about design using glass. Here, I'm going to specifically tell you something about how glass is designed, not as just as manuals or things like that, but how do we really do an authentic structural design of glass? Because this is how I used to I used to design structures when I used to work for the company called Advanced Structures Incorporated in the US. And the third aspect is seismic design of glass. This is again, a very bit of we'll touch upon a bit of seismic, in the sense of earthquakes, and then how glass is designed in earthquake. This is in fact was my specialty, and some of the structures, in fact, we have developed 4 systems when I used to work for the company in the US, and in fact it was presented in a AISC periodical regarding the thing, and I'm glad I got this opportunity to present that paper, which was never presented at this point in time. First, getting on to a brief history of glass. This is my first part of the session out of the 3 sessions. So as you know, the glass history can be, if you really trace back it's 4000 BC in Mesopotamia when it was used for stone beads. The first glass structure was believed to have been made around 1500 BC. Glass in windows was discovered in the Roman occupied Egypt. So this we are talking about 2000 years ago. So polished plate glass was introduced in Britain in the late 18th century. So in the late 18th century. So, and the more importantly, the discussion about glass today we are going to discuss is the float glass. The process of making float glass was introduced by Pilkington in 1959, almost 62 years ago. And it is still the industry standards today. In this process, the molten glass is poured onto a bed of molten tin. Floating on the tin is the molten glass spread out to form a leveling surface. To introduce the structure, one of the first earliest structure, architectural structure or building structure where glass was, became the standard, and it became as like the, normal use of the thing was in 1850 when the glass structure, excuse me. Was used in this building called Crystal Palace, and the architect was he is not called an architect because his name is Joseph Paxton. He was neither an architect nor an engineer. In fact, he was what you call as an horticulturalist, and his inspiration, this is the key thing, his inspiration to design this building was this water lily he found in his one of his ponds. And if you look at the lily, the lily here, it's got this so-called ribs, primary ribs, secondary ribs, and the thin layer of leaf that sticks onto this so-called ribs of this lily. So this was the inspiration for glass, and as I'll show you further, this became the inspiration for your so-called unitized and your stick glazing. And in fact, something major statistics about this structure is it's first major building which was precast and pre-assembled. It's covering an area about 21 acres. it's about 9 lakh square feet of glass, 500 tons of wrought iron, 3,500 tons of cast iron, 33 million square feet of enclosed space. So this was, in that point, it was at point the far ahead of the times for its structure, and especially it was even a glass structure. Now coming back to our current different kinds of glazing system that we have, you all know about this, but specifically it's a stick glazing system. This is the oldest unitized glazing system, point supported glazing system, cable net system. In fact, I'm going to show you a couple of the projects that we were involved in point glazing and cable net, and some of the structures in cable net was one of its kind in the world when it was built. So if you get to the stick type glazing system is where the frame, vertical frame and the mullion. So this is the mullion. So this, if you really look at the Paxton's lily, this is the primary main structure, secondary mullions, and the glass sticks onto this. This has been the traditional method. Of course, it was popularized by the architect Mies van der Rohe, and this is the modernists started to use this as their trademark structure in steel and glass. And the detailing would work like this. And of course, the whole interesting part is these mullions. They per se they are not structural in the sense they are not taking structural load. They are only taking the glazing load. So this is the stick system. And in fact, before to this was Philip Johnson. Philip Johnson was also a student of Mies van der Rohe. He had built one of his own residences. This is again a stick and a mullion system, where you have the basic stick and the glass just supporting onto the mullion. So this is how the stick system evolved. And then we have what we call as the unitized system. So unitizer system is actually what it is a factory made system, where the stick system was used as a modular system and then used for large applications of curtain walls. And here in the unitized system, about 90% of the work of what the glass and everything should be would happen at the factory or at the factory floor. And it is just it comes into a site and it's just pre-assembled. It's faster to do, of course, since it's most of the work is done. And this is very much will be economical and used in very large scale curtain wall projects. And the next evolution was so-called the point supported glazing system. Here, since we were, when I was work for the company, we were the pioneers in doing some of the structures. I would go into some of the history, even though it started in 1960. The concept, the next one is the cable net structure. This is another improvisation after the point supported system. And if you look at the point supported system, cable net and point supported are linked. Of course, the cable net is based on tension cabling as the basic supporting system. It's got, it could be flat, it could be single curved. In fact, it could be even double curved. And in fact, one of the projects in China, which I'm not showing, but it's about 300 feet wall, 100-meter wall. How did it get evolved? In fact, if you really look at it in 1970s or something, 60s to 70s, this so-called patch plate system. So this patch plate system, this is the Norman Foster, Wills Fabers and Dunman headquarters. So it started off as a patch plate system. So if you look at the detail here, this is the patch plate system with four screws. And initially it was not even bolted. That structural point supported glass, which is drilled now, it was not even drilled. It was just has a shelf, and it was just point supported in the sense it was only supported at 4 points. Then it got evolved into what we call as the cable net system. So this is the Kempinski building, which is about 40 meters in width and 25 meters in tall. And in fact, the deflection, in a major wind situation, this whole wall would deflect by about 900 millimeters inside. And this is the typical detail of this cable net. If you really look at it, it's hardly 19 mm cables, 19 mm and 22 mm cables. In this case, it's 22 mm cables, and you could get close to about 97 to 99% transparency. The glass surface would be that, and the shaded surface would be that. Shaded surface would be only 2 to 3%, the opaque surface. This is one of the structures which I was involved in, cable net structures, when I was working for this company in ASI in the US. This is the AOL headquarters. The AOL headquarters is actually the tallest. In fact, today, after the collapse of the World Trade Center in 2001, this is the tallest twin tower structure in the New York, and of course in the United States. And what we were supposed, our scope of work was to design and build this cable net wall, which is approximately 15 meters wide and 30 meters tall. So it is between these two buildings. This is a 15 meter by 30 meter wall. And this is the 15 meter by 30 meter. And this is the interior. And this is the typical cable detail. And I'm just closely show you even the construction procedure. See, this is the truss that was installed at the top of this 100 meter, 30 meter wall. And this truss essentially pulled up all the cables that were coming down from the truss. So this is the cables that's come down from this truss. This is all in pre-tensioned. This is the detailing. This is the cables coming down. And this is the wall. So this wall, I mean, of course, had a deflection of close to even 30 to 500, 300 mm to 500 millimeter in a worst case scenario. This is when the project is complete. So other project that I'm going to show you is this is again a point supported system. It is not drilled glass. It is thin glass. And in fact, structurally, this is one of the only places where we use it as a structural element in the sense as a beam element. Fins are glass fins are used as a beam element, and this is a project we did for Hello in Illinois. And we know about this two kinds of glasses, which is the low iron glass and the tinted glass. And if you notice, this is totally clear, and this is all the glass will have something called as a blue tinge. And how do we avoid that? In case of an aquarium or certain places where you don't want reflection or refraction, we go in for what we call as the low iron glass. Low iron glass can transmit up to 91% of the light compared to a 83% associated with the conventional glass. So this is what a low iron glass would be, 91% transparent. This would be about maximum would be about 83%, and this 83% gives also the bluish tinge. This is the facade wall, and in fact, we were also involved in the roofing of this roof of this structure. The glass fin and the glass wall. So now coming to the interesting part of the thing, I mean the knowledge part of the design of this session. It's session 2. Design using glass. How do we design using glass? First thing is we all know, you all must be knowing, or if you don't know, this is what it is. There are 6 common types of glass. One is annealed glass, heat strengthened glass, tempered glass, laminated glass, insulated glass, and low E glass. In fact, low E glass is only the glass which probably is, it's only a coating. It's not non-structural because it's on top of the glass that is there. Otherwise, we have what we call as a single pane glass. This is a single pane glass. And we have a laminated glass, and we have an insulated IG unit, and an IG unit with a laminated glass. So the question comes is, how do we design this glass? How do we design this glass? Of course, there are manuals and tables that typically we use, but I'll just today discuss in detail the structural design of how do we design these glasses. The first and most important thing is if you were to use a laminated glass. If you were to use a laminated glass, the typical strength that you have to use as the thickness of the glass is only to 75% to 90% of the thickness of a monolithic glass. So if you're using a 10 mm and a 10 mm, 2 10 mm glasses, what you could use is maximum is about only 75%. 75% is a good conservative estimate for design of glasses. And this becomes, why only 75% is because of this inner layer PVB. This does not have the full shear transfer, and depending on the shear transfer of the PEB, glass gets its strength. So using a 75% is the maximum criteria for design of laminated glass. So if the full thickness is there of the 10 mm plus 10 mm, 2 laminate glass, you only use only 75% of the glass. Second, this is an important thing which I want to discuss. In an IG unit, if there is an IG unit, there are 2 glasses, right? There is a glass in the front and there is an air gap. It's not necessarily air gap. It's typically filled with an inert gas. and there is a back glass. So if the glass or two of them are the same size, probably they take the same load, meaning the front glass gets like a load about 100 kg per square meter wind load. This is what it is. If each of these panels would share the same amount of load because they both have the same stiffness. But if the front glass is thinner and the back glass is thicker, it's depending. The stiffness is is proportional to 3 times the. I mean, it's proportional to 3 times the ratio. Hence, the back glass would take up about 90% of the load. So if you were to say if it's 50-50, it goes here, and if you have a 0.5 mm front glass and a 1 inch back glass, probably you get a ratio of about 70% taking by the back glass and only 30% from the front glass. This is one of the load sharing, very important concept that all glass designers should know when they're designing for insulated glass units. Then coming to the actual design, as we discussed, there are 3 kinds of glass: annealed, heat strengthened, and tempered glass. So heat strengthened, we have their strengths all the way up to 600 psi, and for a fully tempered glass we have about 23,000 psi. This is equivalent to almost the strength of steel. The mild steel is about 24,000 psi. This fully tempered glass could get a strength of all the way to 23,000 psi, and of course, and heat strengthened would get you to about 11,000. And the most important part is the part here. Every glass design is based on probability. So what it means is every glass, even though it is designed for the best of the thing, it has a probability of failure. So if we look at this pattern, so if you were to design a glass, the way we used to do this is every glass panel used to be we used to model it using a finite element software like your SAP or your STAT Pro. I mean, it's very simple. All those rectangle panels to point supported glass, everything that can be easily modeled. And then what we used to do is we used to fully load it per the loading condition. It could be wind load or even the dead load or the live load, and then come up with the stresses in the glass for the load. So depending on the stresses, so what this gives is if there is a 6,000 psi stress on the glass, the probability of an annealed glass would be like there are breakage is 500. So if there are 100 glass panels, half of the glass would fail if there is a full loading. And compare that to something like a tempered glass at 15,000, it would only one glass panel would fail. The probability would be like very less. So the way to summarize the design, the way used to work is we take the glass panel, we load the glass panel. I mean, we're talking about this computer model, and get the stresses, actual stresses that the glass would come back, and just come up with a probability. And a probability of 8 breaks per 1,000 is an acceptable probability. So this is the question that comes in. What is the probability that is acceptable? A typical acceptable standard is an 8. So of course, if you're really going for really high we could probably get it to 1, but again, it's not worth it. And again, the safety glass comes in is any overhead glass. This is again also a rule in India also. Per the code is actually every overhead glass should be laminated double glass. Even if one glass fails, the other glass should be able to retain the second glass. And the last type is the low E glass. Low E glass is like the code. This is where probably the environment part of the sustainability part of the glass would come into the picture. What it is typically in a tropical climate like India, glass, we don't want more of light, and in fact we don't want more of heat. Even though we might need more of light, we definitely don't need more of heat coming in. And if you look at the spectrum, I mean the light spectrum, there is this visible spectrum, there is infrared, and of course the ultraviolet. So if you have the VIB-Gaia violet in the one extreme, beyond violet is ultraviolet, and beyond red is the infrared. And the interesting part is all of the heat component that comes in through the glass is because of the infrared. So what this low E coating does is it stops all the infrared rays and it only allows the, I mean, that doesn't mean that it doesn't stop everything. It stops up to about 70 to 70% of the infrared rays, and it allows all the visible light to come in. So what this does is we get in the light and we don't get in the heat, which is what probably in all our tropical conditions that glass, when we use glass, they always say that why do you want to use glass? Because then when there is already, when that would be the cause for heat to come in. So we have a solution here. We need the glass, but the heat part is taken away by the low E coating. So coming to the third part of the session, which is the core of this session, which is actually seismic design of glass. So how do we design glass in a seismic condition? So if you look at the seismic, so I mean, seismic design is a topic by itself. It's like a very big topic by itself. We have seismic design. The main formula comes in is your acceleration of the earthquake, and we have what we call as the acceleration. This G double I is actually the acceleration of the earthquake. Once there is an acceleration, when there is a mass or weight, which is actually essentially when you reduce it to mass, when this mass is excited, there is something called as an acceleration of the earthquake, and this acceleration will constitute what we call as an acceleration in the building. So there is an acceleration, velocity, and displacement in the building. So if you're designing for earthquake, there is this strategy called, you can design based on reducing acceleration, reducing velocity, and of course, reducing the displacement, reducing or increasing the displacement depending on how the design is. So there are three essential strategies for design of earthquake resistant structures. One is displacement based, the second one is acceleration, and the third one is velocity. So essentially, if you really come to the design of the glass, if you really look at the design of a design, or if a glass were to be subjected to an earthquake, glass per se is not a primary structural member, except for, of course, it's a small member by itself. By itself, it's a structural member, but it is not a primary structural member for the building. Glass typically transfers wind and gravity loads. So if there is a glass panel, it transfers wind and its self weight of the glass, which is the gravity weight. It transfers that load into a secondary member and then finally into the building primary structural member. However, during an earthquake event, if the glass is not allowed to move, see, this is the very key thing for earthquake resistant design. If the glass is not allowed to move, then the glass breaks. Then the glass break could happen. So why does the glass break could happen? Is, as we know, I mean, glass is fragile, and we all talked about the probability of breakage. At one point, when the stress increases to the limited that the glass could take, it just breaks. And of course, once it breaks, there is a whole potential for it to be fallen off from its supporting system. So this creates damage, and this is what should be avoided in the design of glass for earthquake resistant structure. So then what is the strategy? So the strategy is, I mean, if people are interested, you could look up to this periodical, ASCE periodical. It's practical periodical on structural design and construction. This was in May 2010. We have our paper. It's high displacement glass seismic system. In fact, 3 glass systems are presented here, which the displacements, high displacement meaning how do we allow the glass to move when the earthquake happens? That is the strategy. So we have 3 here, and in fact, I'll be presenting about 5 projects here. How do we accommodate for this displacements? This is the criteria. This criteria is not, I'm not sure it's still available in the Indian courts, because they are talking about displacement, only displacement. They talk about this, how the displacement of the height of the building should be accommodated, but they don't necessarily talk about the specifically for glass what should be the criteria for design. And again, it's a very interesting concept here, because as we know, there is when there is an earthquake, there will be damage. That a minor damage is acceptable in an earthquake, and as long as it is not life danger, the accepted criteria for design of for buildings in a seismic area is is that the building can take major damages, but it cannot fail. It cannot completely collapse. That is the criteria. This was the criteria before the Northridge earthquake. So when the Northridge earthquake happened, there were a lot of buildings that did not collapse, but lot of glazing systems and systems of glass that went into damage. And the repair of this glazing system and damage to the glass was so expensive that it came up to like 50% to 70% of the cost to replace the buildings. So then there was a committee set up in California to come up with a criteria to ensure that the glass and the glazing system during an earthquake should be designed in such a way to accommodate this kind of drift that happens in a major earthquake. So they came up with the criteria. So this is the design criteria per the code in 2000 in California Building Code, and I assume it is still the same, and because it's a thing. So what they came up with is like the code requires that the cladding system be designed to withstand maximum inelastic drift of 2 to 2.5% of the height of the building. The code also requires that the cladding system for the glass panels and the panel joints accommodate movement of the structure based upon the elastic and the inelastic displacement of the support structure. So what it means is they gave another criteria. So what the other criteria is, CBC's California Building Code states that calculated story drift using the delta M method shall not exceed 0.025% for a story height of a structure of a fundamental period of 0.7 seconds. See, here I want to tell about approximate about what this building period and things like that is. See, we have a earthquake period and we have a building period. Typically, the building period is about 0.1 seconds. I mean, this is only an approximation. It depends on the stiffness of the building. It's about 0.1 seconds per one story. So if you have a 10-story building, it's 10 times 0.1. It would be about 1 second for making the complete oscillation. So if there is a 20-story building, it's approximately about 20 seconds. And if it's like 100-story, it would about 10 seconds and thing. So what they came up with the criteria is 0.7 seconds. So buildings up to 5 to 7 story, they are called as low-rise buildings. So they are supposed to accommodate about 2.5% of the drift. So what it means is if there is a 10 feet tall building, just single story building, it should accommodate about 2.5%, which is like 2.5. I mean, what's that? If it's 100 inches, it will be 2.5 inches. So if it is 120 inches, meaning it is 2.4 or 2.5 inches of deflection. Now, approximately the glass that is there in an earthquake should be accommodate about 2.5 inches for about 10 feet panel. So similarly, for a high-rise building, they reduced it to about 2%. From 2.5%, they came to 2%. And there is for other buildings also, but these two are the primary thing. It's about 2% for very tall buildings and 2.5% for low-rise buildings. So to explain that concept into this project, I mean, this is one of the earliest where the code was used. It's about I think approximately 2002, 2001 is 2001, 2002 is when this building was built. It's a San Jose Civic Center. The architect is Richard Meyer, again, a famous architect in the United States. And we in the sense Architect Advanced Structures Incorporated, where I used to work for, were the structural engineers. So the brief description of this building, it's about totally about 100 feet tall, 100 feet tall from the base to the thing. And the rotunda is about 50 feet and the base is about 50 feet, that's approximately the diameter is 50 feet and the total height is about 100 feet. So what it means is, I mean, since it's 100 feet and of course they had 2% was the criteria, even though we went with 2.5%. So what it means is that it's easier to explain that concept of 2 feet here. So the building is about 100 feet tall. In an earthquake, the top of the building would move by about 2.5 feet from where it is in its original position. And the criteria is nothing should happen to the glass. Of course, this whole was cladded using glass. And the criteria is nothing should happen to the glass. This is the criteria for the code. So what was the structural system we came up with? This is the structural system. It's a cable net. I mean, not cable net, it's cable trusses. front cable, back cable, and then the of course the vertical cable. This is the basic structural system, and of course these cables are supported onto these rib steel beams that are radially all around the rotunda. Yeah, this was our invention. In fact, this was our, in fact we can call it our invention because this was not there before. So you must have, all of you must have seen about the just the point supported glass. It's just a round glass. So what this has is what you call as a slotted hole, and this hole, the slotted hole, is approximately about, it can accommodate that 2.5 inches, because the maximum height of the glass below the rotunda is about 10 feet. So it can accommodate about 2.5 inches of drift. So this is the slotted hole that was created, and this goes on a ball bearing. So what it is it moves within the bearing, within that slot. So what it is this is the bolt for the glass, point supported glass, and this is the slotted hole, and it has a ball bearing, so it just slides through within that hole. So what it is how do we accommodate the drift? So that's what it is, right? So we cannot take the strength. If any forces it takes, it just breaks. So we just allow it to drift. Once it drifts, then it does not get any load. So then again, this is another very interesting criteria in the United States. It is if you have not built anything which was not done before, we are supposed to do a mock-up before this product or a building system is going to be adopted by in the real world. So in fact, this was a mock-up that we did for part of the rotunda. So this is like 2 ribs and about 40 feet tall, approximately 30 feet tall and 20 feet wide, taken as a portion of the dome was taken as to do the mock-up. So this is the mock-up full assembly. And if you see this small yellow thing here, that is a hydraulic jack. That is the jack that would move this whole thing, racket, meaning it just moves this by the same displacement for approximately what the 30 feet is, to ensure that see to that this is a simulation of an earthquake. And this is the actual assembly of the mock-up. This is the mock-up, the actual assembly. And this is when full mock-up was set up. It's got the dial gauges, jet engine, hydraulic jacks. See, this is the hydraulic jack, and this is the jet engine. You might ask, why do you need a jet engine for seismic? No, the criteria was when the earthquake happens, after the earthquake happens and this drift happens, and post this drift, there has to be the wind and water thrown at the glass, and there should not be any seepage. That was the other criteria. So that was the criteria for it. And this is the dial gauge, and this is the final wrecking happened, and this is when it accommodated the full drift. So if you see at the bottom here, the bolt has almost moved to its full extreme end, and the in between, see, look at the drift here. So the glass panels just shingles around, and this is, and we had to use a special silicon here to accommodate that kind of very large displacement. And this is like water being poured at wind through the wind jet, and post that there was no water leakage after this. So the product was successful, and finally this was utilized in the project, and this is the final completion of the project. And this is the final shot of the project in San Jose Civic Center. Yeah, this is project completed. The second system I was involved in is a fin-based system. And again, the criteria was exactly it was only 2% here, because it was only a three-story building here. It was Belmont police station. Actually, this building is Belmont police station, and this is the fin walling system. So how do we accommodate the drift in this fin walling system? Okay, this is the system that we came up with. There are 2 point supported glass here, and there is this rod that takes in the slide. So this slide, so this we are talking about, this will accommodate the 2.5 inches, 2.5 inches or 2.5%, 2 to 2.5% of the drift that comes into comes into this fin walls. So this is our second system. This is again our invention. So if you look at this detail here, this is the fin glass. There are these two bolts. These two bolts are these two bolts. And there is this rod. If you see this rod, I mean, this rod is typically not so much extended in if you look at into all the other structures. In this case, it was extended, and it was of course stainless steel, and it had this rubber bushing on thing so that it could easily slide through and in and out in an earthquake. So this is how a second system was developed to accommodate the earthquake. So the third system that we developed is for a concert hall. And again, there is interesting is, I think IMP were the architects for this, IMP or Caesar Pili. I mean, I'm one of them, I'm confusing. So here is a sliding system. What we have is a structural system like a pipe and a perforated steel T section below. And in the front, there is this sliding system. So how does this sliding system work? These were all our, in fact, initial models when before it went on to the site. Yeah. Yeah. So if you really look at it, this was the portion, and this is the system, aluminum system, which is of course continuous for it's a unitized panel. So this shape, U shape, will go slide within this, say, ball bearing, I mean, the circular bearing kind of a system here. So this was our concept to accommodate this drift in this concert hall structure. So this is the only place you can really see how the system works, meaning, see, you have this slotted system here, U slot here, and a circular plate here, I mean, which accommodates this drift. And again, it's 2 to 2.5% drift. So this is during the construction. Yeah, these are all the main beams that the steel beams going around. Yeah, this is when see this is the place where it had that detail where the whole aluminum channel just slides in and out to accommodate the drift. Yeah, this is when the project is complete. Yeah, this is the project complete. So those were the three projects that had the what I call as the drift, and that was part of the paper. I'm going to show you another two projects where how do we design for seismic. So these are I mean, slightly different from what we call as the sliding system. Here again we accommodate the movement, but the movement is accommodated differently. So in this case, we were supposed it was a project which is an Imperial Bank. This is about a 20-story building, and there was another 2-story building here. I mean, 1 or 2-story building here, 20 feet tall, and we were supposed to connect these two buildings. So connect these two buildings by a corridor lobby. So it's an interesting project seismically, because what we are trying to connect is two buildings which have a different time period in an earthquake. So as I told you previously, the tall building, which is about 20-story, would take about 2 seconds to make a complete oscillation in and out. And the short building would take about only just 0.2 seconds. So how do we accommodate this kind of a uneven movement in two buildings differently? And this lobby is actually connecting these two buildings. So this is actually the lobby passage that connects between a 1-story building and a 20-story building. So how do we do that? So this is again a system of cable net to just the framing system. And the way it works is, it works like a scissor, the way I can explain to you, it's flexible enough so that it just moves in and out. And the most of the detail, that movement happens actually in this hinge. So what it is this is a pin joint hinge at the bottom. So if the building moves, so the pin just slides in and out, and it just accommodates that movement, the differential movement between one building to the other building. So again, it's all about how do we accommodate the building, accommodate the movement. Of course, when you are accommodating, it should also accommodate the joints here where it cannot be a rigid joint. It should be able to flex itself to accommodate the movement that happens during an earthquake. So this is actually one story, and this is a 20 story. So if they both are moving differently, it just flexes itself to accommodate the drift. This is again one of my favorite and probably my all-time best project that I was involved in. This is a canopy that, of course, is again in California. So at the seismic zone 4, I mean seismic zone 5 in India, if you were to say, if we in the California, it's seismic 4, which has got the highest seismic loads coming in. So the project it's a complex curved canopy. So in fact, this is the one of the first. In fact, it was when it was built, and probably I don't know whether somebody tried this again. It is one of the first complex curved glass buildings in the world when it was built, and I'm sure it is not even nobody had tried this anything like this even in the future. Not that I know of. So the interesting part about this is the concept is it has got about 17 pieces of glass. Actually, it had got 18, but eventually it was 17 pieces of glass. And each of this glass is complex curve. I mean, in fact, to tell you about the concept, the architect Eric Owen Maas, their office did was they took a wax, this wax, the candle wax, a lump of candle wax, and they just heated up using a hairdryer, and finally it had some form, and that's how they got their form, and that's how they digitized this into the structure. It is of course I mean, I don't know whether it's call it interesting or whatever it is, but apparently that is how they came up with the form. And it's got this 17 pieces of glass, and each glass is unique. In fact, at that time, Maya, the software that I don't know now, it might have become extinct by all your other things. It's still been taken over by, I guess, AutoCAD. That was introduced then, and we had used the Maya software to come up with the initial form finding. And this was the initial profiling of the glass. So, and this is what it is. Look at the complexity of the glass. Each glass is unique. And of course, we had the problem of how do we, in fact, this is the other thing I should tell you. We have broken all the 17 pieces of glass at one point in our whole process. Sometime it could be at the construction site, sometime it would be during installation, sometime during installation. And in fact, this was our detail to do the seismic joint accommodated using a neoprene pad, but this didn't have enough flexibility. And in fact, there were a lot of glass failures. In fact, this was one of the glass failures. So how did we come up with the design of this? This is, again, as I told you, it was done for one of its kind in the world. The interesting thing is the form was found, and each of the 17 pieces of glass has got a glass mold. So what it is there is a steel mold like this, which is done for each of those glasses that was used there. So there are still 17 pieces of glass. In fact, they had a storeroom to just keep it for some time so that if at all it breaks, there to reuse the mold. So there was a steel mold done for each of those panels. So yeah, this is a steel mold made out of, I think, 4mm steel, and each was taken as each one was a unique mold. Then how do we do it? So what we do is we have this mold. See that this is the other interesting thing about glass is you can only tamper a flat piece of glass. You can never tamper a glass that is slightly, it's complex shape, because the tensioning really happens at the surface. You could probably do it even for bent glass. It is difficult, but bent glass they were able to try and do something. So very difficult to do heat strengthening and tempering for a other than a flat glass. So in this case, of course, we had to use anneal glass. There were two anneal glass, 5/8 to make it into a 3/4. That's about close to 20 mm thick glass, 10 plus 10 glass. And each of this mold had what we call as a flat piece of glass was taken and put it onto this mold on top of it, of course, with differentiator membrane and taken into an oven, and the glass was heated up to about 600 degrees centigrade. So what happens is once the glass gets to about 600 degrees centigrade, it just slumps, meaning it just melts into the position. So that's how we got each of the complex curved glass made from flat glass. And again, since it was a overhead glass, we had to use double glassing and double glass and laminate them together. So this was the process of first bending, getting the glass to its position. And this is when it was taken out from the oven. And of course, it was laminated here. This lamination was another process. And the installation process. And of course, when we did the installation, we had this issue about glass breaking. And this is one of the meetings where we were discussing how do we solve the problem of glass breaking. Yeah, and finally we came up with a detail. And now this is the detail. The detail is this is the catch, the cap to hold the shelf, to hold the laminated double glass, and this is the rod, and this is the thing which can move in and out. So what it means is, yeah, if you really look at this detail, this is the detail for how we came up with the seismic joint. This is the seismic joint. If you look at this thing, it holds, it's like your hand. It can move in and out. In and out. It can move up and down. So it can move up and down. It can just rotate, and there is a neoprene bearing. So what really happens is the glass just floats onto the system here. So if there is an earthquake or any kind of a movement, it within that shelf, it just moves around. And it's the same concept about how do you accommodate the movement. Yeah, as I told you, so this neoprene here will take in and out, up and down. This in and out of the plane is taken here, and up and down it can just rotate. So all the possible actions of movement that the glass can is restrained is released here. This is when it was finally assembled, and again, as I told you, when it was done, it was the one of its kind in the world, as it was a complex curved glass ever done, and with the seismic criteria. So the last thing that I want to show you is an Indian project that we worked on. Again, it's a project where this was a club. We were the facade consultants, me and my fellow classmate architect. He was the architect and I was the glass consultant. So here we had all this circular things that are as part of the facade, and the circular things had a projection and also glass hanging onto it. So again, there are people, this is just below the main walkway, below the footpath as we call it, and any breakage and falling down could easily injure and probably even kill people. So what was done is, in this case, we used the 3M interlayer, and 3M interlayer had the capacity to hold on to the glass even if it breaks. So that was the concept that was used. And this was during construction. All the glass that was used was laminated glass, and even the front circular glass was laminated and in position. And this is when the project was complete. So I guess, yeah, this is hence my session.
Thank you so much for an extremely insightful presentation. And it was very interesting to see all of the projects that you worked on, and we definitely had a lot to learn. Before we end this session, I just had one question for you. Is there any project where you had to retrofit the structure for safeguarding against seismic activity much after the design, much after the construction itself? How was the system used different if you had done it this way?
Yeah. See, what it is yeah, we were involved in one historic, I think some historic project here, and I was not fully involved, but I had an idea about what they were doing. So what they did was, it was the same historic structure, and there was an additional steel supporting structure that was done to it. And the glass system was, one of the glass systems was developed to accommodate that drift. So what it was that structure was already there, and the retrofitting had this steel framing system to have that, and they tried to camouflage the new system and try to make a thing out of it. And of course, the glass was using one of those movement system. They accommodated the drift. Yeah.
All right. Thank you so much for answering that. And on behalf of all of us at Glass Academy, I'd like to thank you again for sharing your thoughts with us today. We will connect with you with questions that may come in from the audience again, and then we'll have your responses up on the website. Thank you.
Okay. Thank you. Bye.